Before we can discuss calculus, we need to introduce an extremely important part of the mathematical language called vectors. Vectors are a very general concept that appears in many forms throughout mathematics. For this class, we're going to be sticking to the basic concepts. Definition: a vector is a quantity that possesses the attributes of magnitude and direction. The most basic geometric representation of a vector is an arrow. More formally, these are known as directed line segments, which really just means that the arrows we draw need to be straight. The pointy end is often called the tip, as in the tip of an arrow, and it's sometimes called the head, as in arrowhead. The opposite end is usually called the tail. Notice how an arrow satisfies the property of being a vector. Each arrow has a specific length, which is the magnitude, and each one points in some specific direction. What's important about this is that it gives us the ability to describe when two of these arrows are the same. Here are two pairs of arrows. In the pair on the left, we can see that they are different because their lengths are different. And in the other pair, the arrows are different because they point in different directions, even though they are parallel to each other. From this, we can intuitively recognize what it means for two of these arrows to be equal to each other. They are equal if they have the same magnitude and direction. Notice that this means we don't care about where the arrows are drawn. We are only looking at the magnitude and the direction. We are now going to think about vectors in the context of the xy plane. If we draw an arrow on the plane, we can describe it by measuring how far in the x and y directions you must travel to get from the tail to the tip. For example, for this vector, you move 3 in the x direction and 2 in the y direction. We denote this vector as 3, 2 with pointy brackets. This is known as the component form of a vector, with 3 being the x component and 2 being the y component. It's very important that you use pointy brackets and not parentheses, as this helps us distinguish points from vectors. The point 3, 2 is drawn in exactly one way, but there are many ways we can draw the vector 3, 2. But just because they aren't the same, it doesn't mean that they aren't related. If we draw the arrow with the tail at the origin, we say that it is in standard position. When we draw the vector AB in standard position, its tip is at the point AB. If we draw the vector that connects the point Q to the point R, we denote this as the vector pointing from Q to R. The notation says this in an intuitive way. If we have the coordinates of the points, we can then calculate this vector by taking the difference. Notice that to get the vector from Q to R, we have to subtract the coordinates of Q from the coordinates of R. This is the ending position minus the starting position. If you're ever not sure which to subtract from which, you can always sketch a simple picture and try it both ways to see which one gives you the correct values. Although we're only working in 2 dimensions for now, vector notation easily generalizes to as many dimensions as we want by just adding in more components. As we've already done a few times in this video, we often use subscripts to keep track of the components rather than introducing more letters, especially when we get beyond 3 dimensions. A quick word about notation. When I write my vectors, I always mark them with a vector symbol above them. The reason is that vectors are a different type of objects than numbers, and this vector symbol reminds me of that. Textbooks tend to use bold-faced fonts for vectors. The reason for this is mostly historical. It used to be very difficult and expensive to typeset vector arrows, but the use of the bold font was readily available as an option. As a student, this always annoyed me a little bit because it was very easy to overlook the bold font, which caused me all sorts of problems. So throughout these videos, I will always use a vector arrow for vectors just to be absolutely clear about what type of object a symbol is supposed to represent. I recommend you adopt the vector arrow for your writing as well. The book has some good exercises to help you build your intuition about what vectors represent and how they interact with each other. We saw earlier how to compare vectors geometrically. 2 vectors are equal if they have the same magnitude and direction. This geometric description is fine for our intuition, but we need to formalize this because while it's good for intuition, it's hard to put into practice in this form. So we will now take a look at that idea from an algebraic perspective. If we represent the vectors u and v using component form, we can see that the only way the vectors are going to be equal to each other is if the corresponding components are equal. Otherwise, either the magnitude or the direction, or possibly both, will not match up. For higher dimensional vectors, we would need all the corresponding components to be equal to each other. The interplay of the algebra and the geometry of vectors will be very important to us as we keep moving forward. And you'll see that we're going to move back and forth between the 2 frameworks in order to make sure that we have a robust understanding of both of them. So far, we've talked about the basic structure of a vector. In the next video, we're going to see how arithmetic and algebraic operations can be applied to vectors.